Hello, and thank you for watching my presentation of the DataTalent Capstone 1 project, analyzing Android malware datasets. I'm going to start by just giving a bit of an overview of the sort of problem, and some issues, and motivations for the project. So basically I would like to analyze publicly available datasets of Android malware and benign software to prepare for the development of machine learning models that will detect malware and distinguish between malware and benign software. And in doing so, I want to identify any potential problems with the datasets, any need to clean the datasets, and then try to do some of the cleaning and get the dataset ready for training models. And I also want to determine data properties and relationships that could be used as like insights to improve those models, to make sure that we have the best accuracy and precision. So a bit of background about why one might want to do this. So two traditional methods for detecting malware are signature-based detection and behavior-based detection. So signature-based detection looks for specific byte patterns that are used to detect malware. So you have some malware sample, you find some byte patterns that are that have good ability to identify the malware. You look for them, and that's how you figure out whether or not it's malware. But this method can fail because people can modify source code through obfuscation, through mechanisms known as polymorphism and metamorphism, and the software won't be detected because the byte patterns change, and therefore you have to constantly update the database of byte patterns to keep detecting new malware and to detect modifications to malware. So it's a little bit brittle. There's also behavior-based detection, and so this uses dynamic analysis and it observes how the application is working. So it looks for things like unauthorized connections, editing files, editing registries, and so on. And this can then detect code if it's been obfuscated. It doesn't rely on specific byte patterns. It's looking for things the application does. But it has a couple of problems. It's quite expensive to do this and to constantly monitor what all software is doing. And it also has a bit of a high false positive rate because many of the things that uh, malware does are done by regular applications. So it's not as precise or as accurate as like signature-based. So another thing that you could look to either replace or add to these methods is heuristic-based detections. So that would be something like a machine learning method. And that would be to learn more generic properties of malicious programs and how they differ from benign programs that you don't want to detect. And so this has the potential to identify threats you haven't seen before and new threats, and do so because you're learning a more generic way of understanding what malware is. So the tools that I use in this project are pandas for data processing. For the charts, specifically stack bar charts, group bar charts, I used Bokeh. But I also had a heat map, and I used matplotlib and Seaborn to do that. The analysis was done in a mix of Jupyter Lab and Google Colab. And I've also put up a repository on GitHub, which is linked to in the slide. So I'll be updating that, or uploading that, and if anyone is interested, you can go have a look at it. One thing to note is that the GitHub viewer for Jupyter Notebooks does not like my file, so it's best to clone it and look at it in Colab or locally. So I'm actually looking at two data sets here, Drebin and MalGenome, as well as a feature data set that describes the columns in each of the data sets. Now this is a pre-processed data set that I got from a paper, Droid Fusion, a novel multi-level classifier fusion approach for Android malware detection, where they had taken Drebin and MalGenome and done static and dynamic analysis to extract a bunch of binary features that are like true or false for manifest permissions, API calls, intents, and command signatures. So these are these were extracted, and they created the data set, and so it's all binary values as well as a class, which is also a binary value of string B for benign and S for malware. So then I started doing some dataset cleaning, so I started investigating a little bit of the properties of the dataset, and I decided to initially to make sure that the datasets conform to the features list that they provided. And when I did this, I found that the Drebin dataset matched those features. When you did a difference between the list of features in the columns, the set was empty. But when I did that with the Malgenome one, I noticed that there were both ones in Malgenome that weren't in the features list, as well as features in the features list that weren't in Malgenome. Now, a couple of them were clearly just format differences. So there was like .system.bin and .system.app that just had to have slashes replaced. So I renamed those columns. But since I didn't have any way to replace those columns in each dataset, I just dropped the missing ones from each dataset so that they would ideally match up and so they could be combined at a later time. I also did some further cleaning because when I was looking at the other properties of the dataset, I saw that while Malgenome had int64 values for all of its columns except for the class, there was actually two object type columns, the class, and it turns out this telephony manager.getSim country ISO column. And so when I looked at the unique types in that, I noticed that it was being interpreted as a mix of strings of 1 and 0, numeric values, as well as question marks. So I found that there was only 5 rows with question marks. And since it wasn't really clear how these should be interpreted, and it was only 5 of them, I simply dropped those rows, and it didn't really affect the total number by any significant amount. And once I was done, the datasets have been massaged enough that they could be concatenated together. I looked a little bit at the dataset to see what class of feature dominated the dataset. So you can see here that most of the features are manifest permissions followed by API call signatures. So those really, really dominate the dataset. But there are intents and command signatures as well. So I did a little bit of further analysis just to understand how much the sample there is and how big the sample is, as well as like how it compares with between each class, the benign and malware samples. And so you can see it's a bit unbalanced. There's a little under double the number of benign samples as there is malware. Now, I mean, most cases that's pretty mild, so it might not even require any additional processing to use it for training a model, but it's something to keep in mind in the future. Then I wanted to look at, since there's so many variables, there's like 210 features that we can look at, I wanted to look at the correlations to see whether or not we could find some that are related. Pearson correlation would often be used, but it works only on continuous values, and these are categorical values, true or false, so you can't use that. So I implemented in Python Kramer's V, which is a categorical correlation method. And rather than, unlike Pearson correlation, which is from -1 to 1, this goes from 0 to 1, where 0 is no association, and 1 is complete association. And so you can see here, here's the matrix. There's so many variables you can't really see them on this, but it illustrates that there are some that are like quite highly correlated. And so I wanted to look a little bit more deeply into that. So in order to do that, I listed the top correlations. And so we can see here that after removing the upper right quadrant diagonal, because those are mirrored from the lower quadrant, I was able to get this list. And what we see here is that there's an awful lot of API calls that are highly correlated. So iBinder, the bind service and connecting services. So these are these are in some way intuitive, that we would understand that they are related calls. And there's also permissions such as permissions such as read and write permissions. Those normally go together, or intent such as screen on, screen off. And those have really high correlations. So what that indicates is that it might be possible to reduce the size of the features by removing some of these highly correlated values, because they're so correlated that if we get rid of them, we simplify any model and make it less likely to overfit to the specifics of the data set. And it does look like we could get rid of potentially a significant number of features and make the model just much easier to understand and much easier to deal with. And ideally better, but that will be tested in the future. I also looked a little bit at the variable frequencies, so I was kind of curious. If we looked at benign samples and malware samples, how often did each feature get used? Would there be some sort of discriminating power? So if they were all the exact same with very little variation, the model would have a hard time potentially learning what malware looks like. But I don't think we have to worry about that, because you can see this little portion of the bar chart, the group bar chart, that there are significant differences between benign and malware variables. So you can see that things like transact and on service connected are far more common in benign software, whereas reading the phone state or sending SMS messages is far more common in malware samples. So this indicates that there's a good chance that we can use these properties to differentiate between data samples, or for new sets of new data sets, and ideally have a high accuracy and precision when we come to building a model. Anyway, so the conclusions: many of the variables are correlated. The data sets can be simplified significantly. API calls are overrepresented in top correlations. They make up the majority of them. There are significant differences in the frequency of variables between the two, so this likely means that they have strong discriminating power. And so my next steps will be to remove these highly correlated variables, as well as experimenting with machine learning models to classify Android programs, and see whether or not we can achieve a model with high accuracy, really good precision, and ideally learn something more about the data. Anyway, thank you very much, and have a good day.